To trap billions of dollars of copper beneath the Earth's surface requires an act of immense, slow-motion violence. Two continental landmasses colliding over millions of years to crush, fold, and elevate a jagged mountain ridge. This produced the Lufillian arc. For decades, standard tectonic models by researchers like Parada and Bierhorst successfully explained the regional framework, the mechanics of how this massive basin formed. But knowing the tectonic history of a mountain range does not tell a geologist where to point a drill rig to actually hit the ore. In 2004, John et al. Proposed that discovering economic copper and cobalt in this region depends on mapping localized structural deformation rather than broad basin history. We must zoom in from the wide regional map down to highly complex zones of intense folding and faulting. To genuinely understand the Zambia Katanga copperbelt, we must reverse engineer the exact kinematic sequence of the Pan-African orogeny. We need to track precisely how tectonic stress remobilized flat, low-grade rock layers into highly concentrated, world-class deposits. Macrotectonic theory provides the geological setting, but it remains strictly academic for industry exploration unless it can be translated into specific, drillable, three-dimensional structural targets. Before the deformation began, the baseline stratigraphy of the Rhone Group was remarkably simple. It consisted of flat, alternating sedimentary layers of sandstone and dolomite. Within these layered sediments, primary mineralization originally formed as widespread, flat stratabound deposits. These early horizontal horizons contained massive total volumes of copper and cobalt, but the metals were heavily dispersed. In this undisturbed state, the ore grades are simply too low to be economically viable to mine. The catalyst for enrichment arrived between 590 and 530 million years ago during the Pan-African orogeny. Massive lateral compression began driving horizontally through the continental crust. Forced inward by these heavy tectonic stresses, the flat stratigraphy buckled. The sandstone and dolomite deformed into sweeping wave-like folds, anticlines curving upward and synclines bowing downward, taking that flat, mineralized horizon along for the ride. The specific geometry of these tight curves is crucial. As the solid rock bends, the hinges of the folds mechanically open up, creating localized, low-pressure dilation zones right at the crests and troughs. This makes compressional folding the first critical exploration filter. The position of those fold hinges dictates both the exact spatial location and the initial thickening of the ore. As the compressional forces of the Pan-African orogeny intensify, the rock mass eventually exceeds its ductile limit. It can no longer bend. Under this extreme lateral stress, the solid rock fractures diagonally, initiating the formation of Lufillian thrust faults. The mechanics of overthrusting are physical and direct. The leading edge of the fractured rock block is forced violently upward and rides completely over the trailing edge. This physical overlapping drives a process called ore repetition. The upward thrust literally stacks the primary stratabound horizon directly on top of itself. Mapping these thrust faults is a mandatory step for economic geologists. Stratigraphic repetition is the primary mechanical method for multiplying the total volume of ore accessible within a single narrow drill footprint. Physical repetition of the rock layers increases the volume, but the intense deformation also completely rewired the deep subsurface plumbing of the region. The extreme tectonic stress fractures the crust vertically, driving deep shear zones that slice straight through the entire stacked stratigraphic package. These shear zones act as vertical, high-pressure conduits. During deformation, deeply sourced, highly heated, metal-bearing fluids are forced rapidly upward through the rock column. When these upward migrating fluids encounter the highly permeable, fractured bedding planes of the Rhone Group dolomites and sandstones, they hit a ceiling. The pressurized fluid bleeds horizontally outward into those specific beds. This triggers a secondary chemical phase, known as remobilization. The newly introduced hot fluids dissolve the original, widely dispersed copper and cobalt sulfides and carry them directly into concentrated structural traps. The chemical result is a massive intensification of metal grades right at the intersections, directly adjacent to the fluid pathways. The copperbelt operates as a distinct two-step system. The initial stratabound deposition provided the raw, dispersed ingredients, but the shear zone fluid remobilization cooked those ingredients into localized, highly concentrated economic deposits. To find the final trap, we have to look beneath the Rhone Group sediments. down into the underlying foundational rock of the continent. Regional tectonic stress drives horizontal compression, while simultaneously forcing rigid blocks of the deep basement rock to uplift into massive domes. This basement dome acts as a hard indenter against the crust above it. It intensely warps and densely fractures the softer sedimentary layers draped immediately over its crest and flanks. These basement uplifts dictate the geometry of local strain. Consequently, the exact contact margins between the rigid basement dome and the softer Katanga sediments serve as a prime structural target for high-grade remobilized ore. John et al. Proved a hierarchy of 5 structural targets: fold hinges, thrust intersections, Rowan shear zones, basement dome contacts, and cross faults. Geologists can't see this 3D architecture directly. Instead, they use advanced surface geophysics to hunt for these 2D signatures. To locate the deep, heavy basement domes, exploration teams deploy gravity residual mapping. They pair this with analytic signal algorithms to strip away the noise of the overlying sediment and mathematically outline the rigid structures below. Over that gravity map, they layer magnetic surveys, processed with fractional horizontal derivative and tilt derivative filters. These specific mathematical lenses expose the hidden spiderwebs of shear zones and thrust faults cutting through the crust. The precise intersection of these 2 distinct datasets, where a magnetic lineament tracing a shear zone crosses directly over a gravity anomaly marking a dome contact, is exactly where an exploration drill rig is placed. In the Zambia Katanga copperbelt, mapping the deformation is entirely synonymous with mapping the ore.